this installment of the GSWA Webinar Series, I will attempt to answer the question, when WAC got in the SAC with NAC, did zircon leave fingerprints? This question arose as a consequence of my compilation of the major crustal boundaries map of Western Australia as part of GSWA's Accelerated Geoscience program, and called into question current timelines for the assembly of Proterozoic Australia. In particular, this question has not been specifically addressed using detrital zircon data from Western Australian basins that are potentially related to this assembly. But first, let's unravel the puns, innuendo, and acronyms to understand what this talk is really all about. The western two-thirds of the continent preserve a remnant of Proterozoic Australia that comprises three cratons: the West Australian, North Australian, and South Australian cratons, colloquially known as WAC, NAC, and SAC. However, I must confess that this talk is very much WA-centric and based mostly on a review of published GSWA data, and since the SAC is not present in WA, my title is somewhat misleading. Rather, this talk is primarily about constraining when the WAC and NAC became amalgamated as a single crustal block. The three currently proposed timelines for this assembly are based mainly on the timing and location of magmatic and metamorphic events, as well as interpretations of their geodynamic or plate tectonic setting. The three most likely timelines for the collision of the WAC and NAC are circa 1.8, 1.7, or 1.3 GA. Note that in this reconstruction, subduction is interpreted to have been beneath the NAC, but as we shall see later, in more recent reconstructions, subduction has been interpreted beneath the WAC. However, in both cases, the evidence for arc-related magmatism in WA is not very robust. If we delve into these timelines in more detail, we find that the earliest the collision could have occurred was circa 1780 MA, which coincides with high-pressure metamorphism in the Rudel province. This early timeline is the most widely accepted, although recent studies conclude that there is no requirement for arc-related magmatism. The younger timeline at circa 1680 MA is characterized by crustal thickening followed by intraplate events, although a collisional setting for this thickening is debatable. The latest possible timing for collision was first proposed by Myers et al. And is now constrained to between 1375 and 1275 MA, and is becoming increasingly accepted as the preferred timeline. The important thing to note about each of these scenarios from a detrital zircon provenance perspective is that each period of orogenic and magmatic activity recognized in the Rudel province is broadly coeval with basin formation on the adjacent WAC. The older Yapunku orogeny and Kalkan supersuite are coeval with the Ashburton basin, whereas extension related to the Krakatini supersuite may be linked to opening of the Edmund Basin. The youngest possible timeline is associated with the recently named Panga orogeny that is broadly synchronous with the Collier and Wongawaban basins and the Camel Suite. But regardless of whether collision was early or late, as represented by these cartoons, the post-collisional basins would be intracratonic, which has important implications for zircon provenance. But before we can evaluate when the WAC and NAC may have amalgamated, it is necessary to assess whether they ever collided at all. The diagram on the right shows a map of Sumerian neodymium two-stage depleted mantle model ages of felsic igneous rocks that highlights an extensive area of relatively juvenile ages between each of the cratons that comprise Proterozoic Australia. This extensive area of Meso and Neoproterozoic rocks with relatively young neodymium model ages compared to the adjacent cratons extends from the newly named Percival Lakes province in the north through the Musgrave province to the Kumpana and Majura provinces, an area that equates to what Kirkland et al. Have referred to as the Merning Ocean. The location and extent of this region of juvenile crust shows that the WAC and NAC are not currently in direct contact, and suggests that they may never have collided at all, which further complicates models of assembly of Proterozoic Australia. A number of features of the new major crustal boundaries map of Western Australia, shown here against a backdrop of isostatic residual gravity, can be used to evaluate the timing of this assembly. Firstly, the inferred maximum ages of the key boundaries between the WAC and NAC indicates that they most likely formed in the Ectasian period of the Mesoproterozoic era. The constraints on the older concealed boundaries, shown by the dashed green lines, are very poor, and they could also have been initiated in the Mesoproterozoic. Secondly, the boundaries have been used to precisely define the extents of the various cratonic blocks within the WAC and NAC, shown in different colors on this slide, that have in turn been used to accurately characterize the zircon age fingerprint of each block, which we will examine later. But first, let's examine the detailed time-space relationships that underpin this amalgamation, starting with those between the Rudel province and the NAC. The time-space plot on the right, taken from the most recent work of Payne et al., shows nicely the correlations between orogenic and magmatic events that are the foundation of all current interpretations. Notice the dissimilarity between the Musgrave province and the adjacent cratons. But now let's look at coeval events on the WAC, starting with basins developed on the southern Pilbara craton margin in the Capricorn origin, where there is a strong correlation between events here and those occurring in the Rudel province. Similarly, on the Yilgarn craton, there is a strong correlation between basins there on the southern margin of the Capricorn origin and those in the Pilbara. And there is also a strong correlation between orogenic events that constitute the Capricorn origin and those occurring in the Rudel province. The location and paleocurrent record of Paleo and Mesoproterozoic basins in Western Australia are critical for understanding the timing of WAC-NAC assembly, because they are potentially either a direct product of collision or intracratonic to Proterozoic Australia. In this talk, I will be focusing mainly on basins developed on the WAC, mainly because less is known about the WA portions of those on the NAC, and paleocurrent directions indicate that basins on the WAC would have a NAC provenance. In the Paleoproterozoic, the most important basin to consider in this regard is the Ashburton Basin here on the southern margin of the Pilbara craton. And in the Mesoproterozoic, there are a number of basins on the WAC, including the Edmund, Collier, Salvation, Scorpion, and Wongawobbin basins developed here in the Capricorn origin. The most important thing to notice here is the potential transport distance from the NAC to the WAC is well within the range of drainages associated with modern collisional belts, and is of the same order of magnitude as the modern-day Gascoyne River. So it is reasonable to expect that, assuming the blocks were in their current relative positions, basins developed on the WAC would have a source area on the NAC. The conventional approach to detrital zircon provenance studies is to characterize potential source areas using zircon age data. In this study, I've used all available GSWA data for each craton as defined by the major crustal boundaries. The data includes both igneous and detrital zircons older than 1000 MA. However, due to the sheer size of the GSWA database, the Yilgarn craton is characterized only by detrital zircons in the overlying Proterozoic basins that have a demonstrable Yilgarn provenance. This approach has generated robust, large-end datasets of the order of many thousands of analyses for the key cratonic blocks, and highlights some of the well-known geological differences between them. For example, the voluminous circa 2.6 GA felsic magmatism on the Yilgarn craton that has no counterpart on the Pilbara craton, which is characterized by felsic magmatism that is older than 2.9 GA. These distinctive zircon peaks can be used to create a barcode for comparison of crustal blocks or for assessment of their contribution to zircon provenance. When comparing these barcodes, it is the location of the peaks that is more important than their relative heights, which are a function of the number of analyses, and consequently peak height is leveled for comparative purposes in subsequent slides. Of particular importance to this story is the difference in zircon barcodes between the NAC and WAC, with the latter represented by the Rudel province on this slide. The Rudel province has a similar zircon barcode to the Pilbara craton, particularly in the interval younger than 2000 MA, that sets it apart from the NAC. A fundamental difference in the barcodes of the WAC and NAC is the age of the dominant zircon peak in the 1900 to 1700 MA age range, with the NAC characterized by an older peak than the WAC. The existence of large, distinct zircon age peaks in the 1900 to 1700 MA age range on these two cratons, combined with their isotopic composition, allows the zircon populations to be precisely fingerprinted, as shown by this lutetium-hafnium isotope plot. Removing the data overlap reveals significant differences in the isotopic and age composition of the WAC and NAC, as shown here by the major magmatic suites. Importantly, the older zircon population that characterizes the NAC is related to younger two-stage hafnium model ages that are absent on the WAC. This fingerprint can therefore be used to discriminate between zircons in the 1900 to 1700 MA age range derived from each craton. Robust application of this technique is currently limited by the amount of available zircon isotopic data, which needs to include detrital samples, as well as acquisition of oxygen isotope from these samples and the NAC. A good analogy for this approach to zircon fingerprinting is what I like to call the Nike incident, which is a classic study in oceanography which came about literally by accident. For those who don't know the story, a container ship ran into a storm in May 1990, losing 21 containers overboard, 5 of which broke open, releasing over 61,000 Nike shoes into the North Pacific Ocean. Over the course of 2 years, these shoes were washed up on beaches all along the west coast of the US, finally ending up in Hawaii in 1992. Because of Nike's excellent logistics system, which assigns every shoe a unique serial number, individual retrieved shoes could be unequivocally traced to the original accident, allowing the ocean circulation pattern to be precisely mapped. This serendipitous study ultimately led to the mapping of all the major gyres in the world oceans. In detrital zircon studies, we know the age of individual zircons, which in our analogy is the same as identifying any Nike shoe. And in this analogy, we often, but not always, also have some information about the circulation pattern from paleocurrents. But it is usually difficult to tie a single zircon or zircon population to a specific magmatic event, as in the case of a serial numbered shoe in the Nike analogy. However, by combining the isotopic characteristics of a zircon population with its age, we have a similar situation to the Nike analogy, which will allow us to track zircons through time and space, and through multiple basin cycles. The fundamental differences in properties such as mantle extraction age and crustal thickness between the WAC and NAC mean that zircons of similar magmatic age from each craton should have distinctly different isotopic signatures, and it is these differences that I aim to utilize in deciphering the timing of WAC-NAC amalgamation. Although the available isotopic data suggests that this zircon fingerprinting technique is workable, more data are required to make robust conclusions in this particular case. Consequently, this webinar mainly addresses the available zircon age data. The most extensive detrital zircon dataset for the Ashburton Basin is this one from Circum 2002, which shows weak source compatibility with the Pilbara Craton and Rudel Province, the Yilgarn Craton, and the NAC. The 3 shaded bars show the age intervals that are most useful in deciphering the zircon provenance. In particular, zircons in the 2100 to 2000 MA age range are typical of the Yilgarn Craton, but atypical of all other sources. The 1900 to 1800 MA age range is atypical of the Pilbara or Rudel and more typical of the NAC or Yilgarn, which may provide possible evidence for an early collision, but a NAC source is less likely because of the lack of an 1870 MA peak, but this needs to be tested with isotopic fingerprinting. The youngest age range from 1800 to 1700 MA is however typical of both the Pilbara and Rudel and the Yilgarn Craton. Samples that make up the Edmund Basin zircon spectrum are from the northern Capricorn origin and are characterized by southwesterly paleocurrents, so there's a good match to the Pilbara Craton and Rudel Province, and a poorer match for the Yilgarn Craton, and a very poor match to the NAC. The dominant zircon sources appear to be the Fortescue and Hamersley basins and minor Pilbara Craton basement, probably through recycling of older basins such as the Ashburton. The dominant young peak at circa 1800 MA is typical of the WAC rather than the NAC. The only sample with westerly paleocurrents is from the Curran member and shows a similar provenance with no obvious contribution from the NAC. However, there is a younger zircon population at circa 1684 MA that may record the middle timeline for WAC-NAC assembly. Unfortunately, the critical timeline for assessing WAC-NAC assembly is represented by a single sample with very few analyses. However, this limited dataset suggests a poor provenance match to the Pilbara Craton and Rudel Province, as well as the Yilgarn Craton and the NAC, although there appears to be a strong contribution from the granitic basement of the WAC, suggestive of uplift in the Patterson origin. However, a better sample of the same unit from Armandola et al. Has a moderate correlation with Pilbara, Rudel, and Yilgarn sources, and a very strong correlation with the NAC. Further characterization of the circa 1860 MA peak is required to confirm a NAC contribution. The age of the Salvation Basin indicates that it likely postdates the youngest possible timeline for WAC-NAC assembly, and since it is characterized by westerly paleocurrents, it should record a NAC provenance. The left panel shows that outcropping Salvation Basin strata have fairly strong provenance affinities with the Pilbara Craton and Rudel Province, as well as the Yilgarn Craton, but weak affinities with the older components of the NAC. However, There appears to be a correlation of the youngest component with the Rudal or Musgrave province, especially the Camel or Wankanki supersuite, although contributions from the Walawuru and Pitjantjara supersuites appears to be absent or minimal. The right-hand panel shows data from drill holes that intersect the Officer Basin basement that show identical results that confirm the presence of the Salvation Basin in this area, which is more proximal to the Musgrave province. A small amount of lutetium-hafnium data is available from Salvation Basin detrital zircons, shown here on the right, which when compared to similar data for igneous zircons from the Rudal and Musgrave provinces on the left, shows that the fingerprinting technique described here can potentially distinguish magmatic zircons with either WAC or NAC parentage, based on their lutetium-hafnium isotope signatures. In conclusion, this review of available data has shown that the major crustal blocks at WA have unique zircon age spectra, and that geochemical fingerprinting has the potential to trace zircon populations in time and space to provide better provenance resolution. There is also no obvious NAC signature in detrital zircon provenance records from Paleo and Mesoproterozoic basins on the WAC prior to circa 1.3 GA. The inferred ages of major crustal boundaries compared with the neodymium model ages and zircon provenance suggest a Mesoproterozoic WAC-NAC assembly. Detrital zircon fingerprints also support interpretations of WAC-NAC assembly at circa 1.3 rather than circa 1.8 or 1.7 GA as previously proposed. And finally, the provenance and tectonic setting of Mesoproterozoic basins on the WAC and NAC are not adequately factored into current assembly models. The next steps in this study are to significantly expand the detrital zircon database in the critical units of the Collier Group and Ashburton Formation, for which samples have already been collected, and to compile zircon data for the NAC from outside WA in order to better characterize this source area. We also need a lot more isotopic data from key magmatic events, especially the circa 1.87 GA event on the NAC, as well as from detrital zircons. Thank you for listening, and I hope that I've been able to convince you that when WAC and NAC got in the SAC, zircon did indeed leave fingerprints.